All right. So, ladies and gentlemen, we're going to finish our discussion about thermodynamics. Yesterday, I posed a few questions to you, and the one I left the class, and it was pretty busy. It was very chaotic. I didn't give you the worksheet last time. I'm going to give it to you today, so we'll be one day behind the worksheet. I'm sure you were broken-hearted that you didn't get any homework last night. But I asked you, consider this scenario. You love your coffee as hot as possible, and you are a very conscientious driver, so you're not going to drink your coffee while you're driving. So you stop at Starbucks, and you pick up your coffee and your cream. You love your cream, but the cream is cold, and you want your coffee as hot as possible. So your two options are this. You either pour in your cream right away, cap it, and drive to school, and then drink it when you get to school. Or you cap it, drive to school. When you get to school, then you open it, pour in your cream, and drink it. You want your coffee to be as hot as possible. Think about this for a second. Should you put your cream in right away when you get it at Starbucks, or when you get to school?
Right away. No, because it'll warm up the... No, I thought about it. So I was talking to Stephen's farmer driving together, and she had the heater on. Well, the heater will warm up my thingy and keep my coffee warm, so I'll just put it in when I get to school.
Your heater's going to warm your coffee to that temperature?
Yes.
You got a hardcore heater.
I like my coffee.
I'm just going to open up
my car.
Let's just pretend that we're actually going to be in survivable temperatures on the way to school. Okay, so let's take a vote. Who says that you want your coffee to be as hot as possible, you put your cream in right away at Starbucks? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Who says you should wait till you get to school to put your cream in? Raise your hand. 1, 2, 3, 4, 5, 6, 7, 8. Wow, right down the middle. Okay, well, consider this. Question? Oh, you mean it doesn't matter?
Yeah.
It totally matters. And I'll explain why. So Newton's law of cooling tells us that when you have two objects in contact, or an object and a fluid in contact, the bigger the difference in their temperatures, the faster heat will flow. Okay? So in other words, you have hot coffee versus warm environment, warm car. The bigger the difference in the temperature between the coffee and the car temperature, the faster the heat's going to flow. Now either way, when you're driving to school, heat's going to leave the coffee and go into the environment. In which case will heat leave the environment faster? Hotter coffee or warm coffee? Hotter coffee. So, if you want to reduce the amount of heat that is lost in the environment, should you cool down your coffee right away or once you get to school? Right away. By cooling down your coffee right away, the coffee will lose less heat on the way to school. If you don't, that 10-minute drive to school, the heat is going to be leaving the coffee, then you're going to cool it down at the end, you're going to end up losing more net heat if you wait till the end. Okay? Does that make sense? Some of you need to convince your neighbor that you were right. Okay, let me go over it again. If you pour in your coffee, your creamer right away, you're going to drop the temperature of your coffee. That's going to reduce the speed at which the coffee loses heat. So the coffee will lose less heat if it is warm than if it is hot. So by cooling it down right away, you lose less heat overall. Because you got to put the cream in either way. Okay? So that's Newton's law of cooling. The bigger the difference in temperatures, the faster heat's going to move. Any questions about that? You implicitly already know this because if you take your 37-degree hand and you touch a 100-degree burner, it's going to hurt. Heat's going to go into your hand. If you take your same 37-degree hand and touch a 50-degree piece of metal, it's going to feel warm, but it's not going to hurt. Heat's going into your hand either way, but heat's moving slower if the temperature difference is less. Okay, so we talked about why it is that the tabletop in our aluminum block would actually melt the ice a lot faster than the wood part of the table or the plastic block, and that has to do with specific heat. Specific heat is a term we use that acts like thermal inertia. Like thermal inertia. Now, who can raise their hand and give me an idea about what inertia is. In your own words, what's inertia? Sean?
Tendency of an object to remain in movement, or its state of movement.
That's an excellent example. Yeah, it's a tendency of an object to remain in its state of movement. A fast object wants to stay fast. A slow object wants to stay slow. A dirty room wants to stay dirty. I like to say inertia is students at a party will remain at a party until acted on by the police. So yeah, objects have thermal inertia too. Specific heat is like thermal inertia. Objects that speed up or heat up and slow down, cool down, fast, have very low specific heat. They have very little thermal inertia. Whereas objects that take a lot of heat to increase their temperature, or give off a lot of heat to increase their temperature, or decrease temperature, they have high thermal inertia. Now I'm not going to go into the molecular ideas about why this happens, but in general, somebody said yesterday, do materials that are more dense, do they tend to change temperature faster? And yeah, they do. Most materials that are very, very dense when the molecules are very close together tend to have very, very low specific heat. They tend to change their temperature very rapidly when the molecules are close together. In general. That's not a rule, but in general. Higher density means a lower specific heat. By the way, the little Cp, the little sub p, means at constant pressure. I haven't seen a specific heat exercise at different temperatures ever. But they still say Cp, and there's like Ct and all the other things. It's just C, little c, specific heat. Does anyone know what the definition of specific heat is? With what I just told you, could you couple one together? Besides thermal inertia. Let me just, okay, Michael.
How fast an object transfers heat?
Pretty good, yeah, how fast an object transfers heat. Excellent start. Can we develop it? Okay. The actual definition is this. It's defined as the heat energy required to raise 1 gram of substance 1 degree. So it is the link between heat energy and temperature. A very strong link, a very big Cp, means it takes a lot of heat to change a little bit of temperature. A very small specific heat means it takes very little heat to change a lot in temperature. Okay. What materials would have a very low specific heat and change their temperature very quickly? Gases? Metals. Yeah, metals. Things, metallic elements. They're very dense. They tend to change their temperature very quickly. You want to make spaghetti with a metal spoon? Yeah, no, because the heat's going to make its way up the spoon pretty quickly. So what materials would have a high specific heat? It would require a lot of heat to change their temperature.
Wood.
Wood? What else? Plastics? What else? Water. Excellent. Yeah. So metals have a very, very low specific heat. They change the temperature very rapidly. And water and most insulators, like plastics and wood, tend to have a very high specific heat. So things that respond to heat change very, very fast tend to have a low specific heat. Those that do so very slowly have a high specific heat. The reason that you can go get your mail in the morning, well, I guess mail is, you can go somewhere in the morning in your pajamas where it's really cold and not freeze to death is because you are made mostly of water. Okay. On the other hand, the reason we don't use a metal spoon to stir our spaghetti is because metals change temperature very, very quickly. You have a mixture, answer your question in a second. You have a mixture of about 50 to 60% water that runs through your engine and then runs through the radiator, that thin thing with the metal with the scooper and the spinning fan in front. Anyway, you have water that runs through your engine to keep your engine cool. The reason water is a really good coolant is it takes in heat, but doesn't change its temperature. It takes in a lot of heat before it changes its temperature up to the boiling point. John?
What does gas have?
Usually very, very low. Sorry, very, very high. Very, very high. Since the molecules are so far apart, they don't ram into each other very well. So Yeah, gases tend to have a very, very high specific heat. When they explode? Some do. But that's not really, that's the realm of not this discipline. Okay. Any questions about this? All right, tomorrow you're going to do a lab. And the lab will be involving calorimetry, where we're going to do the math of specific heat. I'm sorry?
Did you get to burn stuff?
No. That's chemistry calorimetry. This is physics calorimetry. We're going to take really hot blocks, and you're going to take like boiling hot blocks and drop them into cold metal. Okay, there is math for specific heat. Specific heat is given the units joules per kilogram Kelvin or calorie per kilogram Kelvin, depending on if we're using joule for heat or calorie for heat. And it is equal to, the change in heat Q is equal to mass of the sample that's giving off heat, the specific heat of that thing, and the change in temperature. Or as I like to say, MC delta T. Delta Q is MC delta T. Delta Q is MC delta T. Delta Q is MC delta T. MC delta T. Okay. So, yeah.
So, is that joules per kilogram times Kelvin?
Yeah, kilogram Kelvin in the denominator.
Okay.
And then kilogram Kelvin in the denominator in both cases. So hopefully this formula makes a little bit of sense when you think about it, in that if you have a very large sample, it's going to take a lot of heat to change its state. If you have a sample with a very high CP, it's going to take a lot of heat to change its state. And if you want to change the temperature of something a lot, you're going to have to use a lot of heat to change its state. So heat, Q is heat energy. How much heat energy you need to do something is mass, specific heat, change in temperature. To take 1 kilogram of water and raise it 1 degree, it would take 1 calorie, or sorry, 1,000 calories, or 4,000 joules. I'll talk about that in a second. So you take the mass of your water, the specific heat of your water, your goal temperature change, how much do you want to change it, and then you multiply it all together. That's going to be the joules that you're going to need, delta Q. Okay? So tomorrow, you're going to do this really fun lab. We're going to do a lab called calorimetry, where we're going to take hot blocks of metal. The block of metal will be today represented by an orange. And the boiling water will be represented by this beaker of water. So what you're going to do is you're going to get beakers of water, and they're going to be boiling, so the temperature of the block of metals are going to be what temperature? The metal in the boiling water. 100 degrees Celsius. Yeah, so we're going to have boiling water. You're going to extract the hot metal out of your hot beaker at 100 degrees, and you're going to put it in your calorimeter. These are my calorimeters. I made these 15 years ago. They're awesome. They're better than the calorimeters that we can buy in catalogs. It's just 2 styrofoam cups with another plastic cup in there, so the thermometer doesn't go through the bottom of the calorimeter, and then a 3rd coffee cup to act as a lid. They're awesome. They're really good at holding in heat. So what's going to happen is you're going to have some cold water in your calorimeter, and you're going to put your thermometer in there and find out the temperature of the cold water. And then when you move your hot metal block into your cold water, what's the water going to do? It's going to heat up. It's going to heat up because it's drawing heat away from the hot metal, cooling it down. The water warms up, the metal cools down. That is the realm of calorimetry. This is a diagram of a fancy calorimeter that we can buy. It's always double-walled, so there's an insulator inside. And you put some sort of sample in the water. The sample gives off heat. The water changes temperature indicated by the thermometer, and we use the formula. The change in energy, whatever energy is exchanged, is the heat energy the water got, mass of the water, specific heat of the water, change in temperature of the water. And whatever temperature or whatever heat change the water took in, the metal gave off. And that's what we're going to figure out. We're going to figure out which metal gives off the most heat per gram and solve for specific heat. has the specific heat of 4186. Sometimes it's just rounded to 4190 or 4180. Some textbooks say 4184, but 4186 is the specific heat of water. In other words, if I wanted to warm 1 kilogram of water 1 degree, I would need 4 million joules for a kilogram of water. 4,000 joules. 1 times 4186. So 4,000 joules for 1 kilogram of water. Yeah.
Are we going to have to convert joules from calories or calories to joules?
Unfortunately, once or twice. Not on a test, but on a worksheet, yes.
How do we do that?
You realize that, it's a good question, that 1 calorie, 1 little calorie, I had an eraser around here. 1 little calorie is 4186 joules. So 1 little calorie is 4186 joules. By the way, the calories on your Snickers bar are not little calories, they're food calories, which are 1,000 little calories. Yeah, they're actually scientific numbers because what they do is they put them inside a bomb. There's a thing called a bomb calorimeter. I think I mentioned this in chemistry last year. A bomb calorimeter is basically this idea, but they take a little sample of Snickers bar, and then they have this device about the size of a washing machine, and it's sealed down, and they put compressed oxygen in it, so it burns like completely. Compressed oxygen makes everything burn. A lot. Anyway, and then they shock it, and then the stuff basically explodes in the pure oxygen, and they calculate how much heat is given off in the bomb calorimeter. Then they say, okay, based on that amount, a Snickers bar is 260 food calories, 260,000 calories. And someone's like, we shouldn't write 260,000. That's going to use up a lot of ink. They're like, okay, we'll make a food calorie, which is 1,000 normal calories. That's what they did.
Will it be a kilocalorie?
Yeah. Yeah.
So, to get,
Okay, Michael, we'll come back to you if you're thinking.
I know it, I just don't have it.
Michael?
Is the unit for joules per kilogram Kelvin or kilogram Celsius?
Excellent question. It's both.
Okay.
Because we're looking at a delta T, a change in temperature for Celsius is the same as a change in temperature for Kelvin. Because water freezes at 0, boils at 100, change of 100. Water freezes at 273, boils at 373, change of 100. Since to convert between Celsius and Kelvin, we just add 273, a change in Celsius and a change in Kelvin are exactly the same thing. It's an excellent question. Yeah?
Okay, so if we knew they were like 5 calories, we wanted to know how many joules, like that's the reason you could do just times 5 by 4186?
Mm-hmm.
Okay.
Yeah. I would do this. 5 cows, and for every 1 cow, you get 4186 jugs.
So same thing.
Mm-hmm. That's how we do it. Okay. Other questions before we move on? So yeah. So next time when you come in, we'll grab up a thermometer, USB thermometer, and a calorimeter, and a metal block. Yeah. Put them in the calorimeter. Okay. Phase changes. This is really slick. We have to do a little mental exercise here. I keep wanting to come around, but the camera's right there. So here's a mental exercise. When you go to a grocery store to buy a bag of ice, do they leave the ice at 0 degrees Celsius in the grocery store? No. They want you to actually want to have the ice. If your ice is 0 degrees, you put it in the back of your car, it's going to start melting right away. So what they do is they use freezers at about negative 10 degrees Celsius. You get your bag of ice at negative 10, you throw it in your car, drive along on a hot day. What does the ice start to do immediately? No. What's the melting point of ice? 0. So what does it have to do before it melts? It has to warm up. So if you take some ice at negative 10, it cannot melt until it first gets to what? 0. And that's the realm of the MC delta T. This is the formula we use for anything that warms up or cools down. The amount of heat that goes into something is the mass, specific heat, and change in temperature. And if we were to graph change in temperature versus heat added, what do you think this graph would look like to warm something up? With a hand, what do you think this graph would it be? This way? Would it be horizontal, vertical, or diagonal? Horizontal, vertical, or diagonal? As we add heat, what happens to temperature from -10 on? Yep, most of you are giving me something like this, and that's what it would look like. As we add heat to our sample, the temperature is going to rise, and it's going to rise linearly. You know how I know it's linearly? Because when you graph something on a Cartesian plane that's straight lines, it has the formula y equals mx plus b. That's an x. That's a y. M and c are constants. So m and c are your x, and there's your y and your v and m and c. And I realize it's all upside down. You're like, but that should be y. That's I know it's backwards, but 1 over mc is your slope. So the slope has a positive value. Hey, does that idea make sense? Here I'm going to talk too fast. Give me a thumbs up if you're comfortable with what I just said. Okay. So you got your block of ice, you got your bag of ice, it was at -10, you throw it in your back of your car, and it has to warm up to 0 before it starts melting. Now once the ice has warmed up to 0, and it keeps taking in heat, then what's it going to do? It's going to start melting. And here's the really cool thing about phase changes. They are given by the formula delta Q equals mL. Delta Q equals mL. In other words, this has the formula y equals a constant. M is just mass, and L is a constant for that material. It works like this. As the material gains heat at its melting point, it has two choices. It can increase its temperature and become a 1-degree block of ice, or it can have a phase change. What do you think is more thermodynamically favored? A phase change. By changing the phase, you change the entropy. You go from a solid, which has what kind of entropy? Very low entropy, to a liquid, which has what kind of entropy? More entropy. So the ice is like, you know what? I think I would rather become a liquid. And it does. And this is the curve you get. You get a horizontal line where all of the heat that goes into the ice goes to the phase change.
So it stays at 0 until it's melted?
Exactly right. Yep, exactly right. Ever hear that? It stays at 0 until that bag of ice is a bag of water.
Would the already melted water start heating up before the rest of the ice can be melted?
Only if it's far enough away that they're no longer in thermal equilibrium, but we're going to pretend that doesn't happen.
Okay.
We're going to pretend that the cold water and the cold ice stay at 0 degrees because they're in thermal equilibrium. We know that puddles happen and the top of the bag of water might be a different temperature than the bottom of the bag of water, but we're going to assume that they're close enough together, they stay in thermal equilibrium, and they stay at the exact same temperature. Remember thermal equilibrium we talked about yesterday? Okay. Cool. Okay. So it heats up and it melts. Now we have a bag of ice. What's that bag of ice? Or sorry, we have a bag of water. What's that bag of water going to do? It's going to heat up, and what's the curve going to look like? It's going to look like exactly the same. It's going to look like this. Okay. So this is phase change. This is warming or cooling. So warming formula, phase change formula. Warming formula, phase change formula. Expect to use both on an assessment. And expect to be asked what happens to a bag of ice at 0 degrees, what happens to a bag of ice at -10 degrees. One's going to change its temperature, one's going to have a phase change. Okay, and then of course, if it got really hot, if your car was really hot and got up to 212 Fahrenheit or 100 degrees Celsius, then what's it going to do? It's going to boil. What do you think the boiling line looks like? Another horizontal line. In other words, during phase change, as we add heat, the temperature remains the same. So here we're adding heat, temperature remains the same. Until all of it turns into a gas, and then the gas line would be up into like the sky. We can make gases get extremely hot, and they won't phase change until they turn into plasmas. Which is handy, because if you want to drive a locomotive, or you want to drive a turbine in a nuclear reactor to make electrical power, or bring your crops to the market on your locomotive, then you want to get your steam really, really hot. Because really, really hot steam is really good at moving turbines. Hey, does this idea make sense? Okay, cool. We're about to transition to something entirely different. Okay, give me a thumbs up if we're good to go. All right. First law of thermodynamics. Let's have a mental exercise again. It's August. You're cruising down the road. You're going over the bridge or over the hill. You got to go to In-N-Out Burger. And it's 105 degrees outside. And your car is a box to hold in water or hold in hot air. It's 100 degrees. You don't want to roll your windows down because that would make your car less aerodynamic, and that would mean you're going to spend more on fuel. So there's a button you press. This button has only been around on cars for about 30 years. The first 2 cars I owned didn't have this button. What button am I talking about?
Air conditioning.
The air conditioning. So you press this button and magic happens. The first thing you notice is that DJ is falling asleep. The first thing you notice is that what happens to the horsepower of the car? Yeah, you notice it kind of go ooh a little bit. So a little bit of oomph from the car is lost and it goes into the motor. What this motor is doing is it's taking a cylinder of gas and it's squishing it. Because it's drawing a little bit of power from the drivetrain to spin a belt. And when you press a button, it closes the clutch, turning your air conditioner on. And the air conditioner is a little motor, and it takes some gas, and it compresses it. That's why it's called a compressor. Because it compresses gas. And it compresses it. Why? Why would it go to all that trouble to compress some gas? To cool you down. Magically, right? Here's the crazy thing. When you compress gas, the gas gives off heat. When you compress gas, the gas gives off heat. Although it's a really bad analogy, it's like a wet sponge. If you squish a sponge, the water comes out. If you squish gas, heat comes out. It's a terrible analogy, but hopefully it'll work. So when you compress gas, that gas gives off heat. But the machine is under your hood. Who cares what happens under your hood? Why is that valuable? Because you take this compressed gas, you send the compressed gas through a steel coil into this little box right behind your dashboard. And what do you allow the gas to do? Expand. And if compressed gas gives off heat, expanding gas takes in heat. And you blow air over that taking in heat device, and the air becomes cooler. That's air conditioning. You squish the gas gives off heat. You allow the gas to expand, the gas takes in heat. If you blow air over that taking in heat device, called a heat exchanger, then the air that comes out will be cool. That's how air conditioners work. And that's the basis of the first law of thermodynamics. That states mechanical energy and thermal energy are interchangeable through this formula. Delta U equals delta W plus delta Q. We talked about delta W. Delta W is the internal energy, sometimes called the total energy or the total internal energy. Oh, good, the drinking bird's drinking again. A little concerned. Is he okay? His eyes are, he has one eye that's falling off. He's about to be a blind drinking bird. Okay, here's something I mentioned in gases when we did fluids last unit. I'm going to mention again. Work, delta W, is given by a formula that, when we're talking about thermodynamics, P delta V. And I'll show you why. If you take a cylinder of gas, imagine that cylinder of gas has a cylinder head, which apparently looks like this. The shaft that can apply a force on that gas. What is the formula for volume of a gas? For a cylinder. Volume is, for a cylinder, oh my, Mr. Schultz and Mr. Stracken are going to be very upset.
Oh, volume, okay,
Area times distance. So volume of a cylinder is a cross-sectional area multiplied by a distance. Okay?
I'm just trying to figure out the pi, which one, area times distance.
So here's the thing. What is the most fundamental formula for work? The formula for work that you learned back in October? Force times distance. So work is force multiplied by a distance. Well, what is pressure? You learned this last unit. Force over area. I had to apologize, guys. I had no idea I did such a poor treatment of force over area because I was looking at the the final test for fluids, and a lot of people got really easy questions wrong because they didn't do force over area properly. But when you do your test, take a look at force over area. That's pressure. Volume. What is volume? Area times distance. So volume is area times distance, and when you solve out the areas, you get force times distance. In other words, if you want to know how much work that is pressed on the gas, you simply multiply the force that is applied by how far it is applied. Force times distance. That gives you the amount of work that is done on gas or that is done by gas. When we compress the gas under our car engine, we do work on the gas, compressing it. By doing work on the gas says, oh, you did work on me. Here, have some heat. It's tit for tat. Okay? If we are doing work on the gas, it's quid pro quo, something for something. So if we are doing work on the gas responds by giving us heat back. And then we allow that compressed gas to flow in front of Briggs's air conditioner or dashboard, and now we allow the gas to expand. By allowing the gas to expand, the work is done by the gas, and we say, oh, you're doing work on us? We'll take some of our heat, and we give the heat back. That's when an air conditioner works. You compress it, the heat goes out, the work goes in, you allow it to expand, the work goes out, the heat goes in. That's the first law of thermodynamics. Okay, questions about this before we do something even weirder. I realize you're like, my brain is hurting me, and do we need a 1 minute break? Okay, we'll take a 1 minute break. This break has given me the opportunity to put something together. This is called a fire syringe, and it does something really cool. I'm putting a tiny piece of tissue in it, in the bottom, and then into the fire syringe I'm putting a little metal plunger, and on the metal plunger goes this thing to seal it up so it makes it airtight. And I put this plunger on here. I'm using tissue, but eventually, if I get another one, then I'll use nitrocellulose.
Well, that stuff's fine.
Because I don't know if it might explode if you use nitrocellulose. Okay, this happens really fast, and it only happens once. Are you ready? Yeah, it didn't flash. Maybe I'll just use nitrocellulose right now. Give it a try. So your 1 minute break turned into a 2 minute break. And this will be really spectacular. This will be on camera.
I try to do with my mornings, getting up 1 minute.
You're like, dude, did you see that YouTube where Byers blew his hand off? Yeah, that was great. Okay. So again, it's called a fire syringe. And there's something kind of interesting. What happens here is you put a material in the bottom. It smells smoky, by the way. Put a material on the bottom. I'm just going to put a tiny piece of nitrocellulose. Tiny, tiny piece. And hopefully this won't blow up. I am going to be wearing goggles. And I'm going to do it on my side of the desk. So hopefully if their pieces do fall, they won't break very far. Anyway, so if you compress something really fast, like in your air conditioner, then that thing gives off heat. Well, here we go.
Oh, wow.
Hey, it didn't break.
Explosions.
Yeah. Happy days. All right, cool.
Better, that makes me feel better.
Put the whole bag in there. No, it wouldn't fit. Plus, there wouldn't be any something to react with. If I put the whole bag in there, what's it going to lack? Air. Yeah, there won't be any oxygen to burn with. But basically, the fire syringe works because of that rapid compression. That rapid compression causes the air that's inside to give off a lot of heat. Enough heat to light the nitrocellulose on fire. Yeah, we did a really big one. Blow our hand right off. Okay, so this is called a PV diagram. And it illustrates what happens when cylinders are increased and decreased in volume. Now, first and foremost, this little 2/3 of an infinity sign, this means varies with. The thermal energy varies with, or thermal internal energy varies with temperature. Okay? We're not going to do the math. I'm going to spare you of the math until next year in physics. We're just going to get the broad strokes for now. We'll approach the math later. We talked about how work is P delta V. Okay? There's some words that we need to come up with. So far, so good? Now, when gas is compressed, when we compress gas, we do work on the gas. So compression, contraction, or compression gets a positive delta W sign. Does that idea make sense? By doing work on the gas, by compressing the gas gets a positive delta W. If we allow the gas to expand, in other words, the gas does work on us, because we are the observer, then we get a negative delta W. Does that idea make sense? Okay, here's one of the pitfalls. Temperature. If something feels cold, we're the observer. Mr. Observer, Miss Observer, we're the observer. If something feels cold, is heat going into the system or is heat coming out of the system? Think about it. If we are the observer, if something feels cold, then heat is going what? Into or out of? Into. Something that feels cold will have a positive delta Q. Okay? If something feels to us, ooh, this ball feels cold, it must be taking heat from me, the observer, into the system, then the Q would be positive. If something feels hot, that means heat is going where? To us, from the system. So if something feels hot, then Q gets a negative sign. Because we have to think about the system. What is the system doing? Is the system gaining heat or losing heat? Is the system being compressed or expanded? Okay. Now there's some lingo. If no heat goes in or out of a system, which happened here, I compressed it so fast, all the heat had to stay inside the system. It's also a super thick container. We call this adiabatic. Adiabatic means no heat change. Adiabatic. No heat change. Write that down. Your assessment will look something like a matching. Words, description. So adiabatic, match that with no heat in or out. Do not get it confused with isothermal. Isothermal is something different. Isothermal means the same what? Temperature. Isothermal means the same temperature. Iso means the same. Like an isosceles triangle has two legs that are the same, or two angles that are the same. So iso means the same. Isothermal processes have the same temperature. if you have a process where the cylinder head doesn't move, where the gas is neither compressed nor expanded, then we call it isometric, and delta W is 0. A system where delta W is 0 will be isometric. The volume does not change, because work depends upon volume. If you're applying a force, but the cylinder head doesn't compress the gas, then no work is done. So there's isothermal, adiabatic, isometric, and then the last one is if pressure doesn't change, then it's called isobaric. Remember, like a barometer measures pressure? So isobaric is the same pressure. And those are the words you need to know. Isothermal, same temperature. Isometric, same volume. Isobaric, same pressure. And adiabatic, no heat change. Do not confuse isothermal and adiabatic. Now in physics next year, we'll do all sorts of math related to this. But right now, what you need to know is just the conceptual, just what's going on. You don't have to do any math with this. I will ask questions like, heat goes in, volume doesn't change, what is this process? Which we're about to do. Give me a thumbs up if you're ready to move on. We have like 2 more slides, then we're done. Okay, 30 more seconds. I'm so happy now I know I can use nitrocellulose in this thing and it won't kill me. I was seriously concerned that it would shatter and inject pieces of plastic into my stomach. But I'm really happy that we can do that now. It wouldn't have made it to you. It wouldn't have had enough force to get to you. Okay, cool. So moving on. This is called a PV diagram. It's a diagram of pressure and volume, with pressure on the y-axis and volume on the x-axis. And this, inside the PV diagram, is a cycle. Can you see how it's a cycle? This cycle is made of 4 processes. Now, in reality, cycles don't look like this. They look like this. Or they look like chevrons, or they look like crescents. Chevron looks like this. Like that. A crescent looks like that. Okay. So anyway, in reality, they look like crescents or chevrons or crazy. But for our purposes, for our math, they're rectangular. James?
Kind of like a 4-stroke engine.
Yes. Yep. Yeah, the 4-stroke engine has a diagram that looks very much like that. Fuel compression, yeah. And they're everywhere online. You can get tons of diagrams. But we're going to use rectangles because rectangles are easier to do math with. Okay. Process A is 1 to 2. Process B is 2 to 3. Process C is 3 to 4. And process 4 is 4 back to 1, completing the cycle. Let's look at process A. What is remaining the same? Yeah, this is pressure on this axis, volume on this axis. Pressure is remaining the same, so this process is called isobaric. It's isobaric something. That's the adjective. Now we need a noun. What is the gas doing? Look at the volume. Yeah, exactly. The gas is expanding, so this is an isobaric expansion. Because we're at a constant pressure, but the gas is expanding. So that's an isobaric expansion. Okay. Isobaric because it's the same pressure the entire time, and expansion because the volume is increasing. Give me a thumbs up if that makes sense to you. Okay. Any questions? Okay. Look at process B from 2 to 3. What's staying the same? Volume. So this is isometric. And if volume isn't changing, it's isometric. And what is it doing? What is changing? Pressure. Okay. So pressure is going down. So in this case, pressure is going down. here's the hard part. Remember that formula we learned in chemistry and then learned again last year, or last unit, that P1 V1 over T1 equals P2 V2 over T2? Remember the combined law? Well, volume is staying constant, so that means P1 over T1 is a constant. So if the pressure goes down, what's the temperature doing? Also going down. This is isometric cooling. Again, it's cooling because the volume is not changing, the pressure is going down, therefore the temperature also must go down. Now, for those watching on the internet, I realize there's huge nuance here. This is just basic rectangle PV diagram. You'll learn next year if you take physics the nuance and what's really going on. But for the most part, this is all you're needed to know. This is what how to describe it. Okay, so isometric cooling. Now from 3 back to 4 in process C, what is it again? Isobaric, because the pressure is not changing. And if process A was expansion, process C must be de-expansion. Exactly, compression. Isobaric compression. Okay. And then if B was isometric cooling, what is B? Isometric heating. Exactly.
Did you also write warming?
Sure. Okay. Now let's look at the work. Isometric means the volume doesn't change. So in which 2 is there no work being done? Remember, work is P delta V. In which 2 is no work being done? B and D. Good. So delta W equals 0, and delta W equals 0. So the work is all happening in A and C. Here's what's really cool. The net work is the area inside the triangle, or inside the rectangle. So remember, area is just, area of a rectangle is just delta x times delta y. So that's the work. The area is the net work. What we would actually use to make the car go is the area of the rectangle. You don't have to write anything else after that. Because the last thing is the answer to the question. Did anybody research why Willis Carrier got an Oscar without actually making any films? Anyone look at it? I gave you that pun. I said he did something really cool. Okay. Willis Carrier, exactly. Willis Carrier invented the modern air conditioner. And he needed a venue, an advertising space, to sell his invention. What did he use? Movie theaters. It wasn't the popularity of movies that made air conditioners popular in the 30s and the 20s. It was the popularity. One more. It was the popularity of air-conditioned buildings that made movies popular. So what Willis Carrier did is he put his air conditioner into a New York Times, or a Times Square theater, and he advertised it. Come in, away from the heat. Heat in New York is nasty. It gets hot and humid. Come in from the heat. And while you're there, watch a movie. That's what happened. He invented the air conditioning, 1925. He put it in a theater. The theater had tons of population, or tons of customers, and then all the theaters wanted air conditioners. Yeah. It's the 14th. 2/14. Yeah. Happy Valentine's Day.
What is the date?
Build an air conditioner? Yeah, that'd be great.
Build an air conditioner.
Yeah.